Our recent lectures have prepared us to tackle some motion situations using the energy principle. Just to recap briefly, we have discussed how to specify changes to the total system energy, delta E, in the case where the only system energy changes are due to the change in the kinetic energy, delta K. We also learned how to describe interactions using the concept of work, where forces cause energy transfers between the system and the surroundings. Let's now examine two motion cases in detail using the energy principle. Imagine you're outside a spacecraft pushing a heavy box whose mass is m equals 1,000 kilograms. You exert a force F, specified as shown, while the box moves through a displacement delta R, as shown. Initially, the box has a speed of 1.4 meters per second. Questions: how much work do you do? What is the final kinetic energy of the box? What is the final speed of the box? What can we say about the direction of the final velocity of the box? Don't write down your answer to this one, but think about it. As always, it's good to start from a fundamental principle, here the energy principle. Also, from our previous problem-solving experience, it's good to identify the system whose motion we're examining. Here, the system is the box. Now, as we said earlier, when we apply the energy principle, we typically have in mind an initial state and a final state of the system. So it's good to identify those right up front if we can. Here, the initial state is the box at some position when it is moving with the initial speed 1.4 meters per second. And the final state is the box displaced by delta R and moving with some unknown final speed that we need to find. Notice we don't know in this problem what the box's initial position is. We just sketched it starting here, but any place would be fine. However, once we sketch that, then the final position is determined because the displacement is specified. Now, the next key step is to identify the agents in the surroundings interacting with the box. Here the problem implies that you, as the astronaut, are the only agent exerting a pushing force F on the box. So to apply the energy principle, we need to compute the work you do on the box. Notice that in other cases, we could have more than one agent exerting forces. In such cases, we would need to compute the work done by each significant force exerted by each agent in the surroundings, and add up all those works to get what we call the net work. That's the work that goes on the right-hand side of the energy principle. Here we have only one agent, one force, and so only one work we need to compute. Let's do that. Since we have both F and delta R in component form, we can compute the work using the dot product expressed in this form, and we end up with this. So we've answered part A. Now we can address part B, where we use the energy principle directly. Here we have a case where the only system energy change we have is delta K, the change in kinetic energy, which is K final minus K initial. And that's equal to the total work done on the system. K final is the unknown in this part, so we need to solve for it. We found the work in part A, and we can find the initial kinetic energy since we know the initial speed and the system's mass. So we do that. We add that to the work, and we have then K final. Now for part C, we use the definition of K final here. Solve for the unknown final speed, and plug in everything that we know to find that speed. Notice that in this part we solve for the speed, but we can't solve for the velocity. The energy principle is a scalar principle. It doesn't give us any direction information, so in general we can't use the energy principle to solve for vector quantities. Let's do another energy principle example. You hold a ball of mass 1 kilogram in your hand and throw it so that it leaves your hand at a speed of 15 meters per second. Assume that you are the only agent that is doing work on the ball as you throw it. Part A. How much work did you do on the ball? Part B. Assume your throw is directed upward. Using the energy principle, determine how high the ball will rise above the point of release. Starting from a fundamental principle, the energy principle, we identify the ball as our system with the initial state at the start of the throw, when the ball is at rest, and the final state when the ball is just at the moment you release it, when it's moving with speed 15 meters per second. Notice we don't know how much force you applied or what the ball's displacement is. However, we can still compute the work via the energy principle. Here again, we have a case where the only system energy change we have is delta K, the change in kinetic energy, which is K final minus K initial. We can compute that because we know the mass and the speeds. By the energy principle, this is equal to the total work done on the system. From the problem statement, you are the only agent doing work, so that work must be equal to delta K. We plug in the numbers and we can then find the result for part A. Now for part B, we're still looking at the same system, but different initial and final states. The initial state is at the point of release, when the ball is moving 15 meters per second. The final state is when the ball is at its maximum height, which we know happens when the ball transitions from rising to falling. At that maximum height, the ball must be momentarily at rest, so the speed in this final state must be 0. We need to specify the agents acting on the ball. You are no longer an agent acting on the ball because you have released the ball. The only agent that can be acting on the ball is the Earth exerting a weight force. So that's what we need to compute the work that goes into the energy principle, where we can write out the scalar product in component form for the weight force and the displacement. Here we see that the only unknown is the height h, so we can solve for that and we have the result for part B. We can summarize the main steps we used here when we start from the energy principle as our fundamental principle. Given that now we have more than one fundamental principle to start with, you may be wondering how you're going to know which one to use. There are no hard and fast rules, but there are a few guidelines to keep in mind. Typically, if the information you're given includes displacements, then the energy principle is a good starting point. However, if you're given information that involves changes in time explicitly, then Newton's second law is probably the place you should start. Moreover, if you are solving for scalar unknowns, then the energy principle can be used. But if you're looking to solve for a vector unknown, then Newton's second law is where you probably should start. If all else fails, try both. There are cases when you will need to use both. We'll do some examples like that later in the course. The bottom line is that in this course, we should never need to utter the words, "I don't have any idea where to start this problem." Start from a fundamental principle, identify the system, identify the agents in the surroundings that interact with the system, and then go from there. Now don't forget, if you get stuck, you can always bring your troubles to the class forum. Together we'll be able to figure out ways to help you make progress.